At around 190 kilometers per hour, a Formula One car generates enough downforce that it could theoretically drive upside down on the ceiling of a tunnel. That's not a marketing exaggeration. It's a direct consequence of how these cars are shaped, and understanding it means understanding one of the strangest applications of aerodynamics in any sport. An airplane wing is shaped to generate lift, pushing the aircraft up into the air. And phone cars' aerodynamic surfaces are shaped to do the exact opposite. Every wing, vane, and shaped underbody panel on the car is designed to push it down into the track. That downward force increases the grip available at each tire's contact patch, because tire grip scales with the vertical load pressing the tire into the road. More downforce means more cornering speed, more braking force, and more acceleration out of a corner, at the cost of more aerodynamic drag slowing the car down on the straights. Every component on the car represents a negotiated trade-off between those two competing needs, tuned differently for every single circuit on the calendar. The most visible downforce-generating parts are the front and rear wings, inverted airfoil shapes mounted at the nose and tail of the car. The front wing alone typically contributes around a quarter to a third of the car's total downforce, and it does more than just push the nose down. It's the first aerodynamic surface the airflow encounters, so its shape controls how air gets directed to every other component behind it: the side pods, the floor, the rear wing. Get the front wing wrong, and every downstream aerodynamic surface underperforms, regardless of how well those individual pieces are designed in isolation. The rear wing generates its own share of downforce at the back of the car, but critically, it also has to balance against the front wing, so the car doesn't become dangerously unstable at one end during hard cornering. Despite how much attention the wings get, the majority of a modern phone car's downforce actually comes from the floor underneath it, not the wings on top. Since the major regulation change in 2022, cars have used shaped venturi tunnels running underneath the floor, channels that start narrow at the front and expand toward the rear. As air is forced through that narrowing inlet and accelerates through the tunnel, its pressure drops significantly below the surrounding atmospheric pressure. That low-pressure zone beneath the car effectively sucks the entire chassis downward toward the track, generating enormous downforce without adding nearly as much aerodynamic drag as a wing would need to produce the same effect. This is called ground effect, and it's the same basic principle that made underbody tunnel race cars so dominant when the concept first appeared in motorsport in the late 1970s, before being banned for decades over safety concerns and only returning in this modern, more controlled form. Lotus pioneered the original version in Formula One with sliding skirts sealing the sides of the tunnels against the track, generating so much downforce that cars became capable of cornering speeds that made accidents involving loss of that downforce mid-corner catastrophically dangerous, which is exactly why the concept was banned for nearly 40 years before anyone dared bring it back under stricter control. Wings generate downforce, but they pay for it directly in drag, the aerodynamic resistance that slows the car down on straights and costs fuel efficiency. A well-designed underbody tunnel produces a large fraction of its downforce with comparatively little drag penalty, because the air is simply being channeled and accelerated rather than being forced to change direction dramatically against a large wing surface. This is precisely why the floor has become the primary focus of aerodynamic development in modern foam. Teams now spend enormous computational and wind tunnel resources refining the exact shape of the floor's tunnels, edges, and diffuser at the rear, chasing incremental downforce gains that would have seemed trivial in the wing-dominated aerodynamic era of earlier phone generations. It helps to remember that downforce isn't some exotic force unique to racing. It's ordinary aerodynamic pressure difference, the same physics behind how any wing works, just deliberately inverted. Air moving faster across a surface exerts less pressure than slower-moving air, a relationship described by Bernoulli's principle. Shape a surface, whether it's a wing above the car or a tunnel beneath it, so that air is forced to move faster underneath than above, and the pressure imbalance pushes the whole structure toward the low-pressure side. For a wing shaped like an inverted airplane wing, that means being pushed down. For a floor tunnel, it means the entire car being pulled toward the track surface. Multiply that pressure difference across the car's full underbody area, and even a modest pressure differential translates into thousands of newtons of downward force at racing speed. The return of ground effect regulations in 2022 didn't go smoothly at first. Several teams discovered a phenomenon nicknamed porpoising, where the car would violently bounce up and down at high speed on long straights, sometimes badly enough to blur drivers' vision and cause genuine physical discomfort. The mechanism is a direct side effect of how ground effect works. As the car's ride height drops closer to the track, the venturi tunnels generate more downforce, which pushes the car even closer to the ground. But push the floor too close to the track surface, and the airflow through the tunnel actually stalls, collapsing the low-pressure zone and causing a sudden loss of downforce. The car's suspension then lifts it back up, the tunnel reattaches and generates downforce again, and the whole cycle repeats itself many times per second, creating a violent oscillation. Teams spent much of that first season under the new regulations, desperately stiffening suspension and raising ride heights just enough to avoid triggering the effect, even though doing so cost them downforce and lap time. When porpoising proved difficult for teams to solve entirely on their own in 2022, the FIA intervened directly, introducing new technical regulations for the following season that limited how much the floor edges could flex and mandated stiffer floor structures overall, specifically to reduce the aerodynamic sensitivity that caused the worst bouncing. It was a rare case of the governing body stepping in mid-generation to fix a safety and driver health problem, rather than waiting for the next full regulation cycle, underlining how seriously porpoising physical effects on drivers were being taken. The often repeated claim that an phone car could drive upside down comes directly from comparing total downforce generated at high speed against the car's own weight. At sufficient speed, well above the speeds actually reached on most circuits, the total downforce generated across the wings and floor can exceed the car's weight in kilograms of equivalent force. If that much downward force is being generated relative to gravity, in principle the same aerodynamic grip could hold the car against a ceiling instead of a road. Since aerodynamically the car doesn't know or care which direction is technically down, it only responds to airflow and pressure differences. Nobody has actually tested this outside of theoretical calculation, for the fairly obvious reason that there's no tunnel ceiling long enough, and no reasonable way to safely accelerate a car to the required speed while inverted. None of this stays purely theoretical. A modern phone car weighs right around 798 kilograms, including the driver under current regulations, and by the time it reaches roughly 250 kilometers per hour, the combined downforce from the wings and floor can already exceed that entire weight in equivalent downward force. Teams rarely publish exact downforce figures for competitive reasons, but figures leaked or estimated from wind tunnel data over the years have put peak downforce at the car's maximum speed at several times the car's own weight, which is exactly the basis for the oft-repeated ceiling claim. It also explains why phone drivers experience cornering forces of 5 Gs or more in fast corners, forces that would be entirely impossible to sustain on tires alone without the vertical load downforce adds at the contact patch. One counterintuitive consequence of chasing maximum downforce is that it makes low-speed corners comparatively worse to drive relative to high-speed ones. Downforce scales with the square of speed, so at low cornering speeds, where a driver most needs mechanical grip from the tires and suspension, aerodynamic downforce contributes comparatively little. At high speed, downforce increases dramatically, giving the car enormous grip precisely when it's already going fast enough that grip matters most for stability and cornering speed. This is why phone cars can look almost glued to the track through a fast, sweeping corner, yet feel comparatively twitchy and reliant on mechanical setup through a slow hairpin. The aerodynamic effect that dominates at speed simply isn't contributing as much at low velocity. It's worth being precise about why downforce matters at all rather than just being an interesting physics curiosity. A tire's ability to generate cornering and braking grip is directly proportional, up to a point, to the vertical load pressing it into the track surface. Add downforce, and you're effectively adding weight to the car without adding actual mass, which would otherwise hurt acceleration and braking through simple inertia. This is the entire appeal of aerodynamic downforce over other ways of adding grip. You get the benefit of extra vertical load on the tire's contact patch. Without the penalty of extra mass, the engine has to accelerate and the brakes have to slow down. It's effectively free grip, paid for only in aerodynamic drag rather than in the car's actual weight. Formula One gives teams one legal way to deliberately reduce downforce and drag mid-race: the drag reduction system, or DRS. A flap on the rear wing can open in specific marked zones of the track, when a chasing car is within 1 second of the car ahead at a designated detection point. Opening the flap creates a gap in the rear wing's main surface, letting air spill through instead of being deflected downward, and that immediately cuts both downforce and drag at the back of the car. Less drag means a meaningful top speed advantage on that straight, deliberately designed to help a trailing car close the gap and attempt an overtake that would otherwise be extremely difficult given how much a following car's front wing performance is compromised by disturbed air. It's a rare case in phone where reducing downforce, normally the entire goal of the aerodynamicist's work, is temporarily the objective instead. Formula One's governing body has repeatedly rewritten the aerodynamic rulebook over the sport's history, and downforce is almost always at the center of why. Cars that generate too much downforce through underbody effects, as happened in the late 1970s and early 80s, can become dangerously unpredictable if that airflow is disrupted suddenly. For instance, when a car goes airborne or spins, causing an abrupt and total loss of downforce exactly when the driver needs it most. That risk is part of why full underbody ground effect tunnels were banned for decades before returning in 2022 under much tighter, more controlled regulations governing exactly how the tunnels can be shaped. The other recurring motivation is competitive balance and racing quality. Cars that generate too much of their downforce from the wings rather than the floor tend to lose grip when running closely behind another car, whose weight disturbs that wing-generated airflow, making overtaking extremely difficult. Shifting the balance of downforce back toward the floor and ground effect was specifically intended to make cars less sensitive to following in another car's turbulent weight. And by most measurements since 2022, that shift succeeded in producing closer, more frequent overtaking. Because downforce always comes paired with drag, teams don't run one aerodynamic setup all season. A circuit like Monza, dominated by long straights, rewards a low downforce, low drag setup that prioritizes top speed over cornering grip, since there simply aren't many high-speed corners to exploit extra downforce in. A circuit like Monaco, almost entirely tight, slow corners with virtually no long straight, rewards the opposite. Teams pile on as much downforce as the regulations and car will tolerate, accepting the drag penalty because top speed barely matters when the track never lets the car reach it anyway. Between those extremes, most circuits demand a compromise setup, and finding exactly where on that spectrum a given track sits is one of the core strategic decisions every team makes before a race weekend even begins. The next time you watch an phone car take a corner at a speed that looks physically impossible for something with 4 wheels and no wings holding it to the track, remember that it isn't holding on despite the laws of physics. It's exploiting the exact same pressure differences that keep an airplane in the air, just pointed in the opposite direction, hard enough that in theory, gravity becomes almost optional.